All right, let's talk about one of the best comeback stories in AI. It's about how one of the very first AI image generators, a tech that was famous for making blurry, dreamlike messes, managed to completely reinvent itself and become a critical piece of the AI tools that so many of us use today. So, if you've been following AI for a while, you definitely remember the early days of AI art. It all had this hazy, kind of washed out look, right? It was cool, for sure, but you wouldn't call it realistic. But why was that? What was going on under the hood that made it so hard for these early models to create a sharp, clean image?
Okay, I mean, just look at the difference here. It's night and day. Early AI, around 2014, gave us images that looked like a watercolor painting that got left out in the rain. Now, we have modern AI that can generate these hyper-realistic, super sharp images full of texture. This incredible leap wasn't just about getting more powerful computers, it was about fixing a fundamental flaw in one of the original models, the Variational Autoencoder, or as we call it, the VAE.
And that brings us right to the hero, or maybe the anti-hero of our story, the Variational Autoencoder. It was a truly brilliant idea that had this one very fuzzy and very noticeable flaw. You have to remember, back in the early 2010s, VAs were a huge deal. They were one of the first technologies that could actually generate new data from scratch. They were elegant, they were powerful, and they were stable to train, which was a massive breakthrough at the time. They could literally dream up new images. But they had this one persistent problem. As researchers noted back then, yeah, the quality was pretty good, but the images were always blurry. This wasn't some minor bug you could patch. It was a core part of how VAEs worked, and it held them back for years while other models like GANs started making much, much sharper stuff.
So, to really understand why VAEs were so blurry, we've got to pop the hood and see how they actually look at the world. The best way to think about it is like an artist who can only work from a very simple, very specific kind of blueprint.
So what is a VAE, really? At its heart, it's a model that learns by practice. It takes an image, squishes it down into this super compressed, simplified summary, and then it tries to rebuild the original image using only that summary. The better it gets at rebuilding, the more it actually understands what it's looking at. And that compressed summary, that's the key to everything. This whole process has two main parts. First, you have an encoder, which is like an analyst. It studies a picture and creates that condensed blueprint in this sort of abstract idea space we call latent space. Then you have a decoder, which acts like a builder. It takes only that blueprint and tries to reconstruct the image. The magic, and, the source of all the blurriness, was hiding inside that blueprint. And here it is. This is the smoking gun. The original VAEs forced that blueprint to be really, really simple, mathematically speaking. It basically assumed all the rich, complex information in a photo could be summed up by a simple bell curve, a Gaussian distribution. Now, this assumption made the math work and kept the model stable, but it was like trying to describe a skyscraper using only circles. You just can't capture the sharp edges, the textures, and all the fine details that make an image look real. For years, that pretty much seemed to be the end of the line for VAEs. But then, a huge breakthrough came along. It wasn't about changing the blueprint, but about building a radically better architect to read it. Right, so a team of researchers behind a model called NVAE, or Nouveau VAE, decided to attack the problem from a totally different angle. Instead of fighting with the math of the blueprint, they focused on, in their words, carefully designing the neural architectures. Basically, they decided to build a bigger, smarter, and way more sophisticated VAE from the ground up. And they didn't just make a few tweaks. They threw the entire modern deep learning playbook at this thing. They built a much deeper network that could process information at different scales, from big, broad shapes all the way down to tiny details. They used more efficient building blocks to make it faster and added some clever mathematical guardrails to keep the whole thing from falling apart during training. It was a total architectural overhaul. And the results? They were absolutely stunning. NVAE became the first VAE that could actually generate high-quality images at a 256 by 256 resolution. Now, that might not sound huge today, but back then, for a VAE, that was a massive leap forward. It proved the old VAEs still had plenty of fight left in it if you just gave it a better design.
But a better architect was only half of the solution. The next giant leap forward came from changing the very language of the blueprint itself. This led to a brand new question. Okay, what if the problem wasn't the architect after all? What if the problem was the language of the blueprint? What if that simple bell curve was just the wrong way to describe an image in the first place?
And this is where the wavelet transform comes in. It's a classic tool from signal processing, and the idea behind it is just genius for this problem. A wavelet transform breaks an image down into its essential parts, the big, blurry, low-frequency shapes and the sharp, edgy, high-frequency details. It naturally separates the very things that the standard VAEs were mushing all together. And this just illustrates the difference perfectly. A standard VAE blueprint is a single, kind of mushy statistical map. But the wavelet VAE blueprint? Wow. It's this structured, multi-level masterpiece. It has separate, dedicated spaces for the overall structure, for the horizontal edges, the vertical edges, and the diagonal details. It actually speaks the language of images.
And, the proof is always in the numbers. On this chart, we're measuring image quality, and with this particular score, lower is better. A standard VAE is sitting around 32.5, but the wavelet VAE, it drops all the way down to 28.1. That's a significant, measurable improvement in sharpness and accuracy, all because it changed the language it was using. So, with a brand new architecture and a powerful new language for its blueprints, the VAE was finally ready for its comeback tour. And just like that, by combining a better architecture with a way smarter blueprint, the VAE was no longer the blurry underdog. It had transformed into a modern, competitive model, ready to stand right alongside heavyweights like generative adversarial networks and the state-of-the-art diffusion models. So where does the VAE fit into the world today? This table gives us a great snapshot. While diffusion models are still the kings of realism and GANs are famous for their sharpness, just look at the VAE's unique strengths. Their training stability is high, which developers love, and they have this crucial advantage. They avoid mode collapse, which is a problem where GANs can get stuck and just produce the same few types of images over and over. So this comeback isn't just a fun story, it has real-world importance. Because modern VAEs are so stable and reliable, and because they represent the diversity in data so faithfully, they've become incredible tools. They're super valuable for things like data augmentation, where you need lots of realistic variations of something, and even in scientific research, where accuracy and reliability are everything. The VAE's journey from a blurry mess to an AI masterpiece is just a fantastic testament to creativity and persistence in research. By totally rethinking both its architecture and its internal language, a technology that was almost obsolete was completely reborn. It learned to see the details it was always missing, which leaves us with one really exciting question. What new worlds will it help us imagine and create next?